Now let us have a look at properties of asymptotes of a hyperbola. If we analyze x square by a square minus y square by b square equal to 1 hyperbola, we can draw two asymptotes passing through the center like this. It will never touch. We leave a small gap here at this case. This asymptote is y equal to b by a into x. We have proved just now the slopes of this plus or minus b by a, and this is y equal to minus b by a x. Using this, we can define many properties to the hyperbola asymptotes. First one, asymptotes always passes through the center of the hyperbola. Point number 2, asymptotes are common for a hyperbola and its conjugate hyperbola also, because conjugate hyperbola, if you analyze, x square by minus a square plus y square by b square equals to 1 will come for this. And if we take previous condition c square equals to minus a square m square plus b square, and in this substituting 0, m will come as plus or minus same b by a will come. That means asymptotes are coinciding for a hyperbola and its conjugate hyperbola also. Both will have same pair of asymptotes. So asymptotes are common for pair of conjugate hyperbolae. Third one, point number 3. If we analyze, if we observe closely, this slope is b by a, tan inverse b by a is inclination. This inclination is tan inverse minus b by a, which are numerically same but opposite in sign. Therefore, if you take this as theta, this is also theta numerically, but angle between these two will become 2 theta. Therefore, asymptotes are equally inclined to both the axes. Both the asymptotes are equally inclined to both the axes. Not only this, if we observe asymptotes equations, x by a transfer b left side, you are getting y by b. Signs between them will be plus or minus. Taking pair of these two, x by a plus y minus b, x by a minus y by b, multiplying these two, we are getting pair of asymptotes as x square by a square minus y square by b square equal to 0. And hyperbola equation is same, equal to 1. Its conjugate hyperbola same with equal to minus 1 right side. So hyperbola, pair of asymptotes and conjugate hyperbola, all the three are just differing by only the constants, and we can also prove in similar way that these constants are always in arithmetic progression for any other case also, whether it is standard form, simplest cases, shifting cases, or general hyperbolae. We can prove that they are always in arithmetic progression. Therefore, the fourth point is the hyperbola equation, pair of asymptotes and conjugate hyperbola equation are differ by only constants and these constants are in arithmetic progression always. We solve very sensitively lengthy problems in general hyperbola also by using this especially. So this is taken as the fourth point in this. Here, fifth one, angle between asymptotes. Here tan theta is b by a, theta is tan inverse b by a. 2 theta will be 2 tan inverse b by a. Angle between asymptotes is 2 tan inverse b by a, or even we can convert it into secant also. Tan inverse converting into secant inverse, we get 2 secant inverse e also will come. We get a direct relation between eccentricity and angle between asymptotes. A very valid, useful shortcut technique for solving some problems in general hyperbola. So like this, asymptotes always passes through the center. Pair of asymptotes is same for hyperbola and its conjugate hyperbola. Both of them are equally inclined always with both the axes. And one more is this asymptotes equation, hyperbola equation and pair of conjugate hyperbola equation differ by only constants, and the constants of hyperbola, pair of asymptotes and conjugate hyperbola in order are always forming an arithmetic progression. And we can prove many other properties also here by using this asymptotes. Major important fundamental properties here I am just revealing at this stage. We can have one more important part from these asymptotes. If you observe closely the diagram here I am drawing, vertices A dash, these are asymptotes. These asymptotes are dividing the plane of this hyperbola into two important zones according to a requirement. I am taking two zones here. Here first zone is the zone between pair of asymptotes and the given curve. This is taken as the first zone. From any point in this shaded portion, we can draw two tangents to the hyperbola, but the fact is that from any point in this shaded portion, if we draw one tangent like this, surprisingly the other tangent is drawn like this. Means from any point in this shaded portion we can draw no doubt two tangents to the ellipse hyperbola, but both of these tangents will touch the same branch of the hyperbola. Whereas if you take a point somewhere in the second zone, this complete middle part is taken as second zone. Here this dotted portion, anywhere if you are choosing a point in the second zone, here we can draw two tangents, but if we observe, we can draw one tangent touching the right branch, other tangent touching the second branch. So from any point in this second zone we can draw two tangents touching the hyperbola different branches, and from the zone 1 we can draw two tangents which are touching both of them the same branch of the hyperbola. We can also expect question sensitively tested on this particular point. That's why conceptually this point is a valid point to be noted regarding properties of asymptotes here. Now, the general hyperbola, if you are taking, its pair of asymptotes are x square by a square minus y square by b square equal to 0, and angle between tangents is 2 tan inverse b by a. In case if angle between asymptotes is a right angle, you are getting this as 90 degrees, then tan inverse b by a will be 45 degrees, where b by a will be 1 or a equals to b. Conclusion will come. Whenever the length of transverse and conjugate axis are same for a hyperbola, this is defined as a rectangular hyperbola. In this particular case, hyperbola can be defined as a rectangular hyperbola. A rectangular hyperbola is defined as the hyperbola in which asymptotes are perpendicular to each other, or else the lengths of conjugate and the transverse axis are same. This type of hyperbola are called rectangular hyperbolae. Simplest forms of rectangular hyperbola can be converted simply as x square by a square minus y square by a square equal to plus or minus 1. This a square transfer, you are getting x square minus y square equals to plus or minus a square. So, rectangular hyperbola will take this standard form in their simplest forms. Hyperbola and its conjugate rectangular hyperbola, whose eccentricity E will be, I told you already, 2 secant inverse E also give you the same angle. So, secant inverse E is 45 degrees, E will be secant 45, and that secant 45 is how much here? Root 2 we can prove. So, the eccentricity of a rectangular hyperbola is root 2, and the general form of rectangular hyperbola in simplest forms are x square minus y square equal to plus or minus a square. Here, this can be taken like this ordinary hyperbola, looks like ordinary hyperbola, first one and second one. Now, suppose if the axes are rotated through an angle of 45 degrees, if the x and y axis are rotated through an angle of 45 degrees, these axes will be coinciding with the asymptotes positions. That is why if asymptotes are taken as these, if axes are taken in this direction, then you are getting rectangular hyperbola in other standard form also. If we rearrange the diagram in new system, asymptotes will be considered as rectangular axis, whereas hyperbola will come like this in first form, whose equation can easily be traced out from this as some xy equals to c square, and second rectangular hyperbola can be written like this, can be written as xy equals to minus c square. By simple rotation of axis, we can just get rectangular hyperbola equations with the asymptotes as coordinate axis taken as xy equal to plus or minus c square. We can analyze all the properties of this rectangular hyperbola very comfortably, just like other hyperbolic cases. But here, whatever required instantly, we should be able to produce them instead of depending every time on formulae based. We can derive whatever required instantly. So let us have a look at the derivations of all these special rectangular hyperbola cases.